Hello everyone, welcome back on the series on DSP processor. In this video, we are going to explain you how can we use the compare module and extend qualifier units using the Code Composer Studio, and how can we assign the compare module and extend qualifier module and extend qualifier registers using the Code Composer Studio. Okay, with the same, we will implement the pulse width modulation scheme using the TMS320x DSP processor. So before going to start, if you haven't subscribed the channel, please go and subscribe the channel. Contents which we are going to follow in this video, why we need the PWM, and we will see the compare module, all the registers we will look at about all the registers, and later we will see the action qualifier. So with the help of registers and your time-based counter register, time-based control registers, we will see what kind of actions we can take, and we will see the examples, real-time example we will implement. So what is the pulse width modulation? So PWM is a scheme to represent a signal as a sequence of pulses. So for example, we have these original signals and we want to represent this signal into the sequence of pulses. So this is the PWM representation of the original signals. So the output of the PWM is either 0 to 1 and all have the same time period as you can see here, but the pulse width is a different. So for this one, we know what is the PWM frequency, and if we are integrating this part, right, so we can get this kind of average value, and further if we are integrating this part, we are getting this kind of average value. So if we are combining all the points, we are getting this kind of structure with this kind of original signal. So more the frequency we have, more the PWM frequency we have, we are very close to your original signals. So it has a fixed carrier frequency and the fixed pulse magnitude, fixed pulse amplitude, and the pulse width proportional to the instantaneous signal amplitude. Okay, so you can see this is the pulse width, right? And this pulse width is equals to your instantaneous signal amplitude. So this is your signal amplitude, and if we are taking the average of this pulse, we are getting this instantaneous amplitude. So your pulse width is proportional to the instantaneous signal amplitude, and the energy of the PWM energy is approximately equal to your original signal energy. If you find out the energy of this signal, if you find the energy of this signal, we are getting the exact energy of your original signal. So the next is why we need the power, why we are using the PWM with the power semiconductor devices. So the one of the most applications of the pulse width modulation scheme is the digital motor control. If you want to control your digital motor, there also we need a pulse width modulation scheme and digital power supply. It is UPS. If everyone have in their household one UPS, so that is sometimes known as the switched power supply. So they also have the UPS. They also using the pulse width modulations because we want to convert your DC waveform, because in UPS we have a DC waveform and we want to get a 50 hertz and 60 hertz sine wave output signals. So during this case, we are using the pulse width modulation scheme to get a desired output or the desired magnitude and desired frequency. For the UPS, in some countries it will be 50 hertz frequency, in some countries it is a 60 hertz frequency. So by using the pulse width modulation scheme, we are getting the 50 hertz and 60 hertz frequency with the DC source. So we are using DC source and we are converting into the AC alternating current of the 50 Hz and 60 Hz with the help of pulse width modulation schemes. So that's why the pulse width modulation is used in the digital motor control and the digital power supply and UPS and electric drives also. So we know the desired output current and voltage depending upon our applications, which application we are going to use. Either we are using the UPS and we are using digital motor control and we are using the electric drives. So for this, what for this operation we are using the semiconductor devices. So for the semiconductor devices we are using the transistor and IGBT and MOSFET for the pulse width modulation of the power electronic applications. So if you are going for the transistor, IGBT and transistor, so if you are taking the simple example of the transistor, so it is very difficult to operate the transistor into the linear region, that is the proportional region. The reason is that if you are using the transistor into the saturation region, it is generating a lot of heat and it is generating a lot of, it is dissipating the lot of it is the energy is dissipating into the heat, and this is not highly efficient. So we are losing the most of the energy while the conversion. So we are not recommending to use the IGBT and transistor, mostly transistor, NP and PNP transistor, into the proportional or a linear region. So that's why what we are going to do, we are just using the IGBT and transistor in the saturation and the cutoff region. So it is very easy to control your transistor into saturation and the cutoff region. And the PWM is a digital signal, and it is very easy to control using DSP. So now the thing is, we will take an example. We want to generate the desired signal. This is our desired signal, but for this we don't know what is will be the base for this. Okay, so what we'll do, with the help of pulse width modulation scheme, we are getting approximately your desired signal system. So for this, we have the PWM approximation of the desired signals and your input signals. And one more applications of this scheme is that this transistor and IGBT which we are going to use, that is also used as the amplifier. Why it is used as an amplifier? Because your DC supply will be, suppose it is 100 volts, right? And your PWM signal will be, the magnitude will be 0 to 3.3 volts. So it is converting, your PWM signal is converting into this, and this output will be, the magnitude will be from 0 to 100 volts. So it is act as a, the transistor and IGBT and MOSFET act as a amplifier also. Okay, so that's the reason we are using your PWM pulse width modulation with a power semiconductor device. It will amplify your signals, and we are getting our desired output with a desired frequency. So to continuation with this, we are using the compare module. So we have a different set of register. We have a compare A registers and compare B registers to compare the value from the to get the desired output. So now you can now in your mind it can be now you can think like this: compare A and B is similar to, whether it is similar to this A and B. No, this is not similar. There is no relationship between the EPWM X A part and B part with the compare A and compare B. So this should be actually the compare 1 and compare 2, but the Texas Instrument has used the compare and compare B, so we have to use it. Other than this, this has a period register, this is the shadow register, and it has a compare logic. So how can we use this? So the module is to control the active phase of the pulse pattern, and the functionality is based on the compare A and compare B module. And so how many events we can select with this? So the events will depend on your operating modes. So we will see what are the different operating modes. So in the last lecture we have seen that we have different operating modes: up mode, count up mode, count down mode, and count up and down mode. Okay, so in this way, if you are using up and down counting mode, in the previously what actions, at what point we have taken the actions, when your counter registers, when the TBPRD value is equals to 0, during that case we have taken actions. When your time based counter equals to TBPRD, we have taken the actions. Similarly, we are taking the actions as TBPRD, time based counter equal to TBPRD, and time based counter equal to 0. Similarly for the C phase. But here we have four more actions we can take. So if it is up counting mode, we are taking the actions at when compare B equals to TBPRD and compare A equals to TBPRD. When it is the counting down mode, we are taking the action at these two locations, and when equals to counting up and counting down mode, we are taking the actions at these four locations. So we have extra four more locations to take the actions. So what action we can take, we'll see in the next slide, subsequent slides. So these are the different actions. So we are using the EPWM compare. So what are the registers which we are going to use to compare? Okay, we are using two set of registers, compare A and compare B. Okay, so for example, we have this kind of pulse. Okay, this is your compare A. Okay, so this compare A is nothing, this is the numbers. So suppose TBPRD value is 37,500, so it will be approximately, you can consider it is a 10,000 something. So counter A and counter B are just a number. Okay, so it will define at what point of intersection you have to take the actions. Okay, and your compare control register will define, okay, compare control register will define how you are taking the values, how you are changing your compare A and compare B values. Okay, so we will see. So it will control, compare control register will control your shadowing feature. So the compare A and compare B are just the numbers, and compare control registers, we control the operation of the shadow registers. Now what are the shadow registers? So shadow register is the background registers. It can be used to prepare a new value for the next coming period while the current period is still running, or may still relies on the value of foreground registers. So for example, you have one set of registers, and other than this we have the other set of registers. Okay, so you can see it is the foreground registers and this is the background registers, right? So shadow register is the background register. So this register is the background registers, and this registers will prepare the value. So this register will store the value for the next period. Okay, while this current period is still running. Okay, so okay, while the foreground, this is the current register, this is the foreground registers, and this is the background registers. So we'll take a different colors. So this is the background registers. So shadow register is the background register, and it can be used to prepare a new value for the next coming period while the current period is still running. Okay, while in the foreground registers, the value is still relies on the foreground registers. Okay, so how to use the compare control registers? So we want to load the value into from the background register to the foreground registers, and we want to check the status where your background register is empty or it is already filled with the any value. So how can we see, how can we show, how can we check? Okay, so first thing, we are loading the value from the background registers while the current period is executing. So with the help of load mode registers, what can we do? We are copy the value from the background registers into the into the foreground registers. So how we are going to do this? Okay, so we have this foreground registers, and let us suppose this is your background register. So we are copying the value from this registers to this one using the load mode registers. So when we are copying the value from the background register to the foreground registers, when your counter equals to 0, either when counter will reach to the PRD or counter will be equal to 0 and period registers. Okay, so by keeping the load mode values from 0 0 0 1 1 0 1 1, we can transfer the value from the background register into the foreground register. So this is done by the load mode registers. So by keeping the value of load mode registers, we are transferring the value from the background to the foreground. The next thing is shadow mode. Shadow mode features, if you want to use the shadow mode feature, we have to enable it, otherwise we have to disable it if you don't want to use it. So for enabling, we are using the 0 over here over these two registers, the shadow A mode and shadow B mode. And if you don't want to use it, we have to keep it as 1. Okay, so when we are not using the shadowing registers, it will immediately transfer the values into the foreground registers. So there is no shadowing features available. So enable is equal to 0 and disable 1, the background update mode. So the next thing is, we have another set of register, that is the shadow full. So this is the status registers. Okay, so by checking these registers, what can we check whether your shadow register is filled or shadow register is empty. Okay, if this is 1, if this bit is 1, so we can check your shadow register is already filled with another number. And if this bit is 0, so we can check shadow register is empty. Now we can update the shadow register, we can fill the shadow register value, we can fill the background registers value with some other numbers. Okay, so it will show 1 equal to, it will show a shadow is full, and 0 it will show a shadow is not full, shadow is empty. So it is the status build registers, as we already indicate is the status. It will show the status of your shadow registers. Okay, if the shadow is full, it is 1, and the hardware copies the value into the foreground, the bit is cleared automatically. Now the thing is, by default, now when your DSP processor reset, during this case, the by default value will be your shadow registers will be always enabled. Your shadow registers will be always enabled. So this is the important feature for the compare registers. So it will always be enabled. We don't need to use it. We don't need to enable it again. So by default, it will always enable, and the load mode will be okay. So your shadow register will load the value from the foreground register into the background registers during when counter equals to 0. So by default load on the counter equal to 0 and the shadow is active during this case. Now we have a different set of registers. We have a compare registers. Now we want to use it, and when we are passing this compare registers with the TBPRD value, what actions we need to take. Okay, and how can we take the actions so we can generate the two PWM pulse, EPWM1A and EPWM1B. So with the help of action qualifier we can generate this kind of pulses. So what action qualifier modules? So action qualifier modules will do different outputs. It will do nothing. It will clear the output is low, it will set the output, and it will toggle the output. So how it is doing this and what point it is doing this? So we have a different set of points. One is this one is this one is this one. So we have a four set of points. One is 0, one is TBPRD, one is compare A and compare B. So for EPWMA, when counter is 0, okay, time base counter is 0, during this case we are making the EPWMA is high, and when it will reach to the compare A value we are making it as low. Okay, and again high and again low. Similarly for the EPWMB, when the counter is equal to 0 we are making it is high, and when counter will reach to the compare B we are making it low. So it will follow the same pulse pattern. Okay, so it is for one PWM frequency. So this is the moving pulse. So this is the same case but in different way. When for EPWM we are generating when your TBPRD value with time based control register, the compare A value will be equal to TBPRD. It will generate, it will be making high, and otherwise it will making low during this at this point. Other than this, we have a different independent modulation on the compare and compare B for up down counting modes. So let us suppose this is the one pulse and this is the another pulse, another set of pulse, right? So this is for compare A and this is for compare A. Okay, these are for the compare A and these are for the compare B. Okay, so this is the up counting mode. When for EPWMA, how can we generate a pulse for this pattern? When your counter is up counting mode and it will reach to the compare A value. During this case we are making it as 1, and when it is down counting mode and your compare equals to TBPRD value, we are making it clear. It will follow the same pulse pattern. Similarly for the B also, it is follow the same pulse pattern. So how can we use this? Okay, so these are the actions we have taken, but there should be some set of registers. With the help of set of registers we can take these actions. So there will be action qualifier, control output B, A and B. Okay, so these are the set of registers which are going to follow. So how can we use it? So let us suppose we have a up and down counting mode. Okay, and we have two different, one is compare A and one is compare B, right? So we have a different operating, different positions, different events. One is, I'll take different colors. One is at this point, one is at this point, one is at this and this. So we have at 6 points. So one is a 0, you can see here. The second one is period, this is this one. Okay, so this is up counting mode, right? So this is up counting mode and this is compare A. Okay, so CAU will indicate counter compare value of A during up counting mode. Okay, and when it is down counting mode, so this is the compare value. So compare value of A during down counting mode, CAU and CAD. CAU compare of A using when counter is up counting mode, and compare with A when counter is counting down mode. So during this case what actions we need to take? Okay, similarly for B also it will follow. So what are actions we can take? So we can take this kind of actions. Okay, at 0 point, at 0 when time is counter equal to TBA, when TBPRA time is counter equal to 0, we can take 0 0 1 0 1 1 0 1 1. So we can make it do nothing. We can make pulse set clear, and we can make pulses set that is high, and we can make a pulse means it will whether it is low to high, and when it is both high then we can make it low. So with the help of this we can make it high or low. So for example we will see it with the example. So we will take only up counting mode. Okay, so it is up counting mode and this pulse we want to generate. So this is one is the counter. So how pulses we are getting the pulses? So like this we are getting the pulses. So actions, where we have taken the actions, we have taken the actions at 0, this point and this point, 0 and compare A, right? So 0, what actions we have taken? We are making it high. So we are making high means 1 0. Okay, period, we are doing nothing, so we are keeping it 0 0. And this is the counter up mode, right? So counter up mode, we are making it clear, so it is 0 1, and this is 0 0 0 0 and 0 0. So it will be how much? This is 4 bit, this is 4 bit, this is 4 bit. So it will be 0x 0 0, this will be 1, and this will be 2. So it will be by using the TBPRD, by using the action qualifier value, by using the action qualifier value, we can keep this value, so we'll achieve this kind of pulse pattern. Okay, so now we'll see with the example. Now we will generate the 1 kilohertz square wave signal at EPWM1A with a variable duty cycle, and duty cycle will vary between 0 to 100%. So this is the pulse width modulating. We are modulating the pulse width between 0 to 100%. So what are the registers which we need? We need a TBPRD, time based control register, compare, and action qualifier, and this is the formula for using up down counting mode we are using. Okay, so we will see in the real-time applications, and we will come back here. So this code is for pulse width modulation schemes, as we discussed previously. So here we are just going to use to demonstrate the two modules, like compare modules and the action qualifier modules. So here we are using the pulse width modulation. So for that we need to initialize the setup for EPWM1. So we are just generating the pulse from the EPWM1 only. Okay, and we are just using the CPU timer 0, so we can increment and decrement of your pulse with while going to the CPU timer ISR. Okay, so we are just going down, and here we are initializing the CPU timer period. So here we are initializing the 150 megahertz your port frequency and 100 microsecond. So at each 100 microsecond, it will this program will go into the ISR, and it will update the value of the compare registers. So the next is we just define the GPIO registers. If you want to learn more on GPIO registers, you can go on my previous videos, link given in the descriptions. Now the basic part is the EPWM units, so it is given here. So you can see we want to generate the 1 kilohertz PWM frequency. So depending upon the clock division and high speed clock division and the counter mode. So here we have chosen the up down counting mode. So it can be 1 0 0 1 and 2, 0 0 0 1 and 1 1 0. So we have chosen 1 0, that's the decimal equivalent of 2. So it will indicate we have chosen the up down counting mode, and the high speed clock division we have made x 1, so it will divide by 2, and the clock division we have made 0, so it's divided by 1. So by the calculations with this, we can calculate the TBPRD value is 37,500 at 150 megahertz clock frequency. So now the thing is the action qualifier value which we have taken, like during up counting mode and down counting mode, we have calculated the action qualifier value from the previous slides, as we have mentioned. So it is calculated as 0x 0060 from the previous slides. As you can see, as you can take the videos back, and you can check how can calculate the action qualifier values for the up down counting mode. So next is initially we want the 100% duty ratio. So here the EPWM registers dot compare A dot half dot C compare this. So it will be like 37,500. So initial value we are making it down from 37,500, so we can achieve the 100% duty ratio first. So now we have to update the value. So every time we have to go to the CPU timer ISR. So in the CPU timer ISR, what we have initialized? We have initialized the static integer, that is up down equals to 1, and this is for the Watchdog timer. We have cleared the Watchdog timer, and good key and valid key using this. So our main code will start, the main logic will start from here. So if you want variable pulse widths, so if up down equals to 1, so if this condition is true, it will goes to this inner loop, and in this inner loop also it will check if EPWM register dot compare value dot this compare value is less than the TBPRD value. So here we have a TBPRD value is 37,500. So if suppose the compare value is 0, if suppose compare value is 0, we are incrementing the compare value, otherwise we are making in the counter 0. If this condition is not true, then we are making the up down value is equal to 0. So when up down, okay, so when up down value is equal to 0, again it will go out of the loop and it will check if up down value is 0. Okay, so this condition is making false, so it will go in this loop. So in this loop again it will check if EPWM register's value is greater than 0. Okay, yeah, greater than 0. So what it will do, it will decrease the compare value, it will decrease the compare value. So otherwise it will make the up down equals to 1 and again it will go. So this loop is repetitive, so the pulse field will be 0 to 100% and 100% to 0, compared to 100% to 0 and 0 to 100%. Okay, so this is the basic program for variable pulse width generation from the EPWM1 registers. So now as you can see in the left side of the window, we have to add this much of the files. So how can we add these files? We can go to we can just right click on with the help of mouse and you can just go to the add files. With the 8 files, you can go to the TI control suite, device support, F2833, version 133. There could be different versions, you can see here. There could be version 122, 132, 132 version 133. So, and here we are using the common files. In the common files, you can see the sources. So these are the files which we are going to add. Okay, other than this, where you can go to the include, okay. You can go to the header files you can go to source. So this file also you have to add and to the project, and here you have to add the non-BIOS setup from the project. So after adding these files, so all the files will come here as you can see. And one more thing, you have to go to your properties and just right click on this. So it will go in general, you have to select what is the variant. So it is showing different variants. So I have a Dell 2833X board and the processor which I have is 28335 and the connections which I have connected with my DSP is XDS Texas Instrument XDS 100V2 USB debug Pro. And okay, and one more thing, you have to go to the include options and you have to add these two files also. Okay, so include header files and one is the common files you have to add with the project and make it okay. Okay, now we will run this. So here it is running, you can see here it is running the program. So if there will be some error, it will show some kind of error. Okay, so now there is no error in the program. Okay, so now we will debug this test and we'll just check whether code is working fine or not. Okay, so we just resume this code and we can see on the DSO as I'm running. So I'm recording the video from the mobile. So I'll focus this video on the from mobiles to the DSO. We'll see. As you can see here, we are recording the videos. So your pulse width is varying from 0 to 100%. At this frequency you can see here is a frequency of 1 kilohertz, and this pulse width is varying from 0 to 100% as we have mentioned in the code itself. If you have any queries, you can contact me throughout the YouTube channels, and you can comment me on the comment section regarding next videos. Thank you.